Hello, my name is Jonathan Rubin and I am a postdoc at UCLA. My research is in equivariant homotopy theory. More specifically, I have done work on Elmendorf Piacenza type theorems and infinity theory and equivariant category theory. I often focus on combinatorial and categorical aspects of equivariant homotopy theory. Indeed, I find these sorts of problems intrinsically interesting, and their solutions often have interesting homotopical implications. In this video, I will describe some of my research and some of my plans for the future. So I'd like to start with the Elmendorf Piacenza theorem. Equivariant homotopy theory is the homotopy theory of spaces and spectra equipped with an action by a group G. For the purposes of this discussion, let's assume that the group G is finite. In equivariant theory, we frequently study the fixed points of G actions, and these have a certain amount of structure. For suppose X is a G set, then for any subgroup H, we have a set of H fixed points. For any inclusion of subgroups, we have a reverse inclusion of fixed points. And for any subgroup of G and group element, we have a multiplication map between our fixed points. All told, we get a presheaf over the orbit category OG, whose objects are orbits G mod H and whose morphisms are G maps. Let's denote this presheaf by 5x. Now one can play the same game with G spaces, and in this context we have the following fundamental result due to Elmendorf and Piacenza. Namely, the functor phi from G spaces to orbit presheaves induces an equivalence of homotopy theories. Analogous theorems have been proven in other contexts. In particular, Bowman, Mazur, Osorno, Osornova, Ponto, and Yarnall proved the analog of the Elmendorf-Piacenza theorem for G categories, and May, Stefan Zakharevich proved an analog for G posets. In my joint work with Guillou and May, we gave general conditions for when the Elmendorf-Piacenza theorem holds for actions by a Hopf group. Now, a Hopf group in a symmetric monoidal category V is a group object in the category of co-commutative comonoids in V. Hopf groups can act on other objects just as groups can, and we have the same equivariant formalism that we're used to, including this functor phi. Under mild conditions, which ensure that certain model category structures exist, we have the following theorem due to Guillou, May, and myself. Namely, if phi, the functor phi, preserves the colimits appearing in the construction of cell complexes, then the Elmendorf-Piacenza theorem holds for actions of the Hopf group. We then specialized to homological and simplicial contexts, and in particular, we obtained an Elmendorf-Piacenza theorem for modules over co-commutative differential graded Hopf algebras, in the usual sense. I'd now like to turn our attention to n-infinity theory. So let's continue analyzing the fixed points of a G action, but introduce some algebra. Suppose M is a G module under addition. Then phi of M is an orbit presheaf, but we have more structure. Indeed, we can use addition to construct transfer maps such as this sum below, where we sum Gx over the elements of the group G. Now this sends an element of M to the G fixed points of M, because for any element H times this sum is equal to the sum of hgx by equivariance, and this is just equal to the original sum by the strict commutativity of addition. Now, the interesting thing is that transfers also exist in homotopy commutative settings, but the recipe I just gave breaks down because we no longer have strict commutativity. In this context, transfers are extra structure, and this leads to the notion of an n-infinity algebra. Roughly speaking, an n-infinity algebra is an equivariant object equipped with a homotopy coherent associative unidal and commutative operation together with a compatible system of transfer maps. More precisely, n-infinity algebras are parametrized by n-infinity operads. These are symmetric operads equipped with a G action such that for every n greater than or equal to 0, sigma n acts freely on On to the gamma is either empty or contractible for all subgroups gamma of sigma G cross sigma n, and On to the G fixed points of On are non-empty for all n greater than or equal to 0. The G fixed points of an n-infinity operad correspond to the ordinary operation, whereas the gamma fixed points more generally correspond to transfers. Now, the set of transfers parametrized by an n-infinity operad O form a combinatorial structure called a transfer system. These are partial orders on the subgroup lattice of G that refine the inclusion relation and are closed under conjugation and restriction. In this case, we think of relations as transfers. Now, a theorem due to Blumberg and Hill is that there is a full and faithful embedding of the homotopy category of n-infinity G operads into the lattice of G transfer systems. Moreover, Blumberg and Hill conjectured that this embedding is actually an equivalence of categories. This was since proven true in independent work of Bonventuri Pereira, Gutierrez and White, and myself. So the theorem now is that the Blumberg and Hill conjecture is true. In other words, the homotopy category of n-infinity G operads is equivalent to the lattice of G transfer systems. This has the effect of reducing the homotopy theory of n-infinity operads to pure combinatorics. I'd like to sketch the idea of my proof of surjectivity. We start by building the free discrete operad D on the desired transfers, and then we attach cells to make D into an n-infinity operad. This second step is basically formal. There is a functor E that sends the empty set to the empty space and sends every non-empty set to a contractible space. Applying E to D level-wise gives the desired n-infinity structure. Now, the hard part is showing that D has no extra transfers, and to do that, I computed the fixed points of a free operad. This is a non-formal computation because one must apply a right adjoint to a left adjoint. I'd now like to turn our attention to equivariant category theory. So there is a categorical analog of the operad ED where we replace E with a functor tilde, which has the property that tilde of the empty set is the empty category, and tilde of every non-empty set is a contractible groupoid. D tilde is a categorical n-infinity operad, and it makes sense to ask what its algebras are. So non-equivariantly, Siegel and May show that the classifying space of a symmetric monoidal category is an E-infinity space, and we expect something similar to be true equivariantly. So in the equivariant context, one can use normed symmetric monoidal categories. These are ordinary symmetric monoidal categories equipped with norm maps that satisfy a single coherence axiom relating them to the ordinary product. Now the theorem due to myself is that algebras over D tilde are in a one-to-one correspondence with normed symmetric monoidal categories equipped with a suitable system of norm maps. Remember, D is constructed freely from a certain set of transfers, and we need to use the same data to construct our normed symmetric monoidal categories. It is essentially straightforward to check that a D tilde algebra is an NSMC. You just look inside the operad and find the diagrams you need. The hard part is showing that a D tilde action arises from the generating data in a normed symmetric monoidal category. Here the idea is to reinterpret Maclane's classical coherence theorem operatically and equivariantly. Now, two upshots I'd like to mention are that the classifying space of a normed symmetric monoidal category is an n-infinity algebra, which gives us a method of constructing n-infinity algebras from a small amount of algebraic data. Second, normed symmetric monoidal categories interpolate between the equivariant symmetric monoidal categories of Guillaume, Merling, Azorno and those of Hill-Hopkins. The equivariant symmetric monoidal categories of GMMO are input to infinite loop space machinery, whereas those of Hill-Hopkins provide a language for describing index monoidal products of the sort encountered in Hill-Hopkins-Ravenel's solution to the Crevere invariant 1 problem. I'd like to conclude by describing what's on the horizon. So I want to continue probing equivariant homotopy theory from this combinatorial and categorical perspective, and one long-standing project of mine is to prove an n-infinity version of Thomason and Mandel's theorem that symmetric monoidal categories model all connective spectra. More precisely, I'd like to prove that normed symmetric monoidal categories model all connective O spectra in the sense of Blumberg and Hill. Here an O spectrum is an equivariant spectrum equipped with some but not necessarily all additive transfers. Now, the natural thing to do would be to try to adapt Thomason and Mandel's proofs, but unfortunately we can't do that yet because we do not have the necessary technology. Thomason uses lax symmetric monoidal categories, whereas Mandel uses gamma spaces, and the n-infinity analogs of these structures are not yet well understood. So developing this technology is a place to start on this problem, but there's plenty more work to do. I'm excited to get on it. Thank you very much for your attention, and thank you to the organizers for holding this event.